Okay, so I'm going to talk about excited state, mainly solving the Bethe-Salpeter equation. And if, well, time allows a little bit, I can also focus a bit on time-dependent DFT. So let's get started. Being one of the last speakers, I would like to wrap up also a little bit what you have heard so far and put it in the context of what is coming now. So what is the state-of-the-art methodology that we are working on? You had a lot of talks about ground state calculations, density functional theory, where we solved the single particle like Conchem equations. And in order to do better, to go to excitations, we have to go to many body perturbation theory. And this gives us access to the band structure, what is eventually measured in photoemission. Now, the process that we are discussing here is, this is a band structure. You have a fully occupied valence band, which is indicated by this electron sitting here. You have an empty conduction band, and now you shine in light with a high energy, and this light would kick out an electron, and this gives you access to the information about the valence region. Likewise, you can bring in an electron in, let's say, inverse photoemission, and the excess energy goes out in form of light. And this gives you access to the conduction band region. And if you combine these two, you get information about the total band structure, and in particular on the band gap. Now, how you do this? You do this with the GW approach. This is what Patrick Rinke has been talking about. So in essence, you start with these Conchem eigenvalues here, and you update these eigenvalues by computing the matrix elements of the self-energy operator. You subtract what you have already accounted for in terms of exchange of correlation effects, and this way you get the quasi-particle energies. Now, if you want to do spectroscopy, so computing absorption spectra or things like that, you have to go even higher up in methodology, because you would like to describe a different process again. And this process is demonstrated here. So again, you have the band structure here with the full valence region. You shine in light, but now the light has less energy than in the photoemission experiment. And the electron is just taken to one of these empty conduction states. But what we need here is to account for possible electron-hole interaction, because this electron that is exciting and is sitting now in the conduction band, it may well feel the hole that it itself has left behind. And this could give rise to even bound electron-hole pairs. So how do we describe this? We stay within many body perturbation theory, but as said, we have to go one level higher up. And this means we have to solve what we call the Bethe-Salpeter equation. So what we explicitly introduce here is a term in the Hamiltonian which takes care of the electron-hole interaction, besides treating this many electron, many hole system, which can be treated by the methodology lower above. And what we get then is the energies of these electron-hole pairs and the coupling coefficients between the electron and the hole. Now, let me get just a minute back to the ground state here to explain what we have done so far. I mean, to get to the Conchem equation of density functional theory, so to get to this one electron equation, we have done a trick. Because DFT is a many-body theory in nature, but why can we solve a single particle equation? Because we have replaced this system of interacting electrons, every electron interacting with every electron, by a system of non-interacting particles, but this system is fictitious. So these electrons don't talk to each other anymore, but this comes, of course, with a price. And the price you have to pay is that these Conchem energies and the wave functions cannot be interpreted anymore, because it's just an auxiliary system. Now, this is okay, but it's not necessarily what we want, because, I mean, single particles are very dear to us. It's much easier to think about an electron that moves here, or an electron that's exciting, rather than thinking about the whole electron cloud at the same time, all the electrons. So what we would like to have is a description of the many-body system in terms of single particle-like states, but these states should be interpretable. And this can be reached by many body perturbation theory, by introducing this quasi-particle concept. So again, we start from this system of interacting electrons. Think about a photoemission process where we shine in light. After some time, you will realize that this light of high energy has ejected an electron. In other words, it has left a hole behind. And if you again look at certain time, you see that the system has been polarized, and this polarization is time dependent. So if you look it up, then probably the hole has moved here, and some of these electrons have followed this hole, and the whole electron cloud has rearranged. Now this is what Patrick has introduced already. It's just a repetition here. But it's very important to mention a few things here, because what is important is the screening, and the screening is dynamical. So if you, for instance, consider this picture here, this electron is sitting very close to this hole, so it feels this electron-hole attraction very massively, whereas the same electron here doesn't feel the same attraction of this hole, because there's other electrons, the electron cloud in between, which has screened this electron-hole interaction. So, and you can consider now this hole plus this screening cloud as a new particle. This is the quasi-particle concept. So what are the key players? The key players here is the dielectric matrix, because it gives rise to the screening, and it's the dynamically screened Coulomb interaction W. So this is the W which appears in the GW approximation. So why do I mention this? Because screening is also important in the electron-hole interaction. In this case, it's not the electron-electron interaction that's screened, but now it's the electron-hole interaction, again the Coulomb interaction, that is screened. So how do we get this quantity, this screening matrix? And this brings us to light-matter interaction. So we basically look at the response of a system to an external perturbation, and this external perturbation is the electric field. In this case, it's the electric field of the light beam. So for instance, we can expand the polarizability in terms of the components of this electric field, and the coefficients in here is the so-called response function. And you can get in a linear approximation, so if you just focus here on the first term, you can get this response function, the susceptibility, the conductivity, the dielectric tensor. You can get all of this in the same way by just looking up which of the quantity you would like to expand. So most important, as I said, is the dielectric function or dielectric tensor, which relates the D with the electric field. Now, if you look into a little bit more detail, you see that this is a quite complicated term, because it's non-local. Of course, you can perturb your system in one space, and then you look up what the response in the different spaces, but it also depends on the time. So this is a dynamical quantity. So, but it's typically not what we compute. What we compute is most of the time the Fourier transform of it. So you have this dielectric tensor now dependent on Q, which is the momentum transfer, and omega, the frequency of the incoming light. And of course, it's also dependent on the polarization of the incoming and the outcoming light beam, which gives rise to these coefficients alpha and beta here. So how do we compute this? Now, this is where we get back to our quasi-particle picture, because here we have to take care of another quasi-particle, and these are these electron-hole pairs, these excitons. So let's get to these neutral excitations. Again, this is the process that we would like to describe, the interaction between the electron and the hole. And the new quasi-particle now is the exciton, which is formed by quasi-electron and the quasi-hole. So you need to do this GW calculation before, in order to get this quasi-particle band structure, before you start coupling these two guys to each other. So you could consider this exciton also in a very simple model, because it's just a positive charge and a negative charge, so it looks like a hydrogen atom with an effective mass. And very important here in this simple model, you can describe the binding between the electron and the hole in terms of this very simple formula. And you see already here that the screening, the dielectric constant here plays a role. So the stronger the screening, the less bound this electron-hole pair will be. So, and this brings us back to the beta equation. This is the equation we have seen already. This gives us the energies of the electron-hole pairs and also the coupling coefficients. But it also gives us access to the two-particle wave function. So this is the wave function which now depends on two particles, on the position of the electron and the position of the hole. So it's a pretty complex six-dimensional object. And how do we compute this? I mean, actually we know from the ground state calculation, of course, all the wave functions, at least the Conchain wave functions, or you can also do it in GW, the wave functions of the conduction bands and the valence bands. So the valence bands now play the role of the hole, and the conduction band states play the role of the electrons. And now we can take all the states that we have from the ground state and build all possible combinations of them, and that way we have an ansatz for a two-particle wave function. And if we solve this, we get these coupling coefficients, which tells us then how strongly coupled this electron and the specific states in such an electron and hole pair is. So this is another way of writing down the beta equation. This is already in matrix form. Here you see the electron-hole Hamiltonian. And you see from the indices, this is quite an involved object, and that's why it's also very time-consuming when you compute it. So what is inside this Hamiltonian? There are three terms. First of all, it's the simplest one, it's the diagonal term. What does it tell us? It just tells us what the distance at a given k point, the conduction band and the valence band have from each other. So this is basically the term that plays a role if you switch off the Coulomb interaction and just look at independent transition. So it's just a direct transition from the valence band to the conduction band. But if you switch on electron-hole interaction, there's two more terms coming into play. The first one, the direct term, and this is attractive. This really makes the Coulomb attraction between the electron and the hole. Because it's quite cumbersome to compute. It scales basically like Hartree-Fock, has this four wave function inside. But very important, in contrast to Hartree-Fock, you see that this term is screened. So here again, you have this Coulomb potential, but this Coulomb potential is screened by the dielectric matrix that comes into play here. So this gives rise to the binding, but we have another term, and this is counteracting, and this is the exchange term, which is repulsive. So one basically shifts the spectrum to the left, the other shifts it to the right, where in most cases, at least in, let's say, in semiconducting cases, this attractive term wins. So this is stronger than the other one. This term is also called the local field effects. So from the screening, you could also already guess how important this electron-hole interaction is in different systems. So in metals, you have very high electron densities, so the electrons are very well screened. That means that electron-hole interaction hardly plays a role there. But in semiconductor insulators molecules, so the larger the band gap is, or the smaller the electron density is, the less efficient is the screening, and the more important this attractive term will be. So, well, and then looking up these coefficients here, you could also think about what the cost of such a calculation is, because it scales with all these valence bands, the conduction bands, and the number of k and k prime pairs you have. So let me stay one more minute with these equations here. So these three terms give rise, if you take it into account, to spin singlet excitations. So you have all these terms here, but you can, with the same formalism, also describe spin triplet excitations by just switching off this exchange term. So a triplet doesn't feel exchange, so it's only the attractive Coulomb term which counts. And of course, then you can imagine that the binding energies of triplets are larger because you don't have this term that's counteracting. However, if local field effects don't play a role, then they also can have a similar strength. So going back to the singlets, we can also probe then other methodologies. So this is costly, as you know, so you could imagine that you may get away with a cheaper method to compute your spectra. And you can probe this by just again switching off different terms. So for instance, if you switch off the attractive term, then you get what we call the random phase approximation. So it's just a direct transition including local field effects. And if you now switch off also the local field effects, both of them, then you're getting to what we call the independent particle approximation. It's just really the transitions between the electron valence and the conduction band, and these transitions don't see each other. They don't have any connection to each other. So I will sometimes show you this independent particle approximation in examples just to highlight how important the electron-hole effect is. And this is very important to probe because this is something only theory can. We can switch off an interaction and switch it on again, but experiment can't. So we can tell, let's say, experimentalists how important Coulomb interaction is in excitations. So now, how does this affect the optical spectra? Let's have a quick look at the dielectric function. In the independent particle approximation, it's pretty simple. So we have this delta function here, which tells us basically the energy conservation. So you just need a light frequency of light that fits between the valence and the conduction band, then you will have a peak in this dielectric function, given that the selection rule allows it, and the selection rules is given by this momentum matrix elements. So now, looking at the dielectric function that you get from the Betisal-Beta equation, it looks very similar, but there are two distinct differences. One is that the peak positions obviously are not anymore at the distance between valence and conduction bands, but they are now at the energies of the electron-hole pairs. So what you could expect going from this approximation to the real thing is that your peak positions would shift. And then there's another effect here, because you see that these matrix elements, which were the pure momentum matrix elements before, they also get renormalized with respect to the coupling coefficients. And this basically gives rise to a redistribution of oscillator strength. So thinking again, if the electron-hole interaction is not important, then these electron-hole pairs will be basically this same energy, like the difference between electron and hole energies. Then the peaks will stay the same or will only slightly shift. And then also these coupling constants will be close to either 0 or 1, and you will get back the independent particle approximation. Now let's have a look at an example for these two effects, or two different examples, of course. So one example is silicon. Silicon is, of course, a material with a relatively small band gap, so the screening is still rather efficient, not quite, so you have excitonic effects, but you don't find a new peak, so a strongly bound exciton here. So if you look at the random phase approximation or the independent particle approximation, doesn't make a big difference here. And then you go to the solution of the Betisal-Beta equation, you see that the oscillator strength is redistributed, but there is no new peak, no strongly bound exciton appearing below here. In contrast, if you look, for instance, at an organic crystal, and this is a one-dimensional polymer ordered structure of polyacetylene, so it's basically a zigzag chain of carbon atoms with some hydrogens at the end. There you see a very, very strong renormalization of your spectra, going from the independent particle approximation to the BSE. So this is what I said before. If you have a strongly bound state, then the peak position will shift, and you can basically read from this shift here what the binding energy of the electron and the hole is. So it's not an absolute number, but it gives you an idea how strongly bound these are. So these are prototypical examples which gives you somehow the range of binding energies that we can have. So they range from 0 to, let's say, 1 electron volt or even more. And in order to demonstrate this, I've brought a few examples that I would like to discuss with you. So I stay with organic materials, organic crystals, three-dimensional materials. In this case, I think in the previous talk you have just seen this pentacene crystal. Pentacene is very important for organic electronics. It has a, I would say, decent mobility, much larger than many others. It also shows singlet fission, so it's a very, very important molecule here. Now, you can create these molecules, a chemist can, in different lengths. So you start from the smallest one, which is naphthalene, anthracene, tetracene, and pentacene. All of them form the herringbone crystal structure, so there are two molecules in the crystal. And I would like to point out here how strongly the electron-hole binding depends on the size of the crystal. So it also depends on the molecular packing. We will see this later, but here I would like to demonstrate the dependence on the molecular size. Now look at the independent particle approximation first. You see, when going from a small molecule to a larger one, that the peak position shift, and this is just reminding you that the band gap of the large molecules is much smaller than the band gap of the small ones. So this is nothing to be worried about, or nothing particularly important. What is important in view of exciton interaction is that if you look now at the spectra that have been computed by Bethe-Salpeter equation, then you see that they also shift to the left because the band gap is changing, but the shift is less pronounced. You see here, this shift in anthracene is 0.7, in naphthalene is 0.9. If you go higher, it's becoming smaller and smaller. And we may ask the question why this is the case. So, as you see here, typical singlet exciton binding energies, they are in the order now of 1 electron volt, or between 0.1 and 1 electron volt. So these are cases of very strong exciton binding. And triplet states are even more localized, more confined. So they have binding energies of up to 2 electron volt even. We will see later an example with even higher energies. Now, so let's ask the question why this is the case. And in order to do so, we have a look at the electron-hole wave function. So as said, this is a complex object, 6 dimensions, so we cannot plot it in the 3 dimensions we have. So we have to play a trick, and the trick is this, that we just fix the position of one of them, so we fix the position of the hole, and then we look at the distribution of the other. And this is shown here for the short molecules, for naphthalene. So we have put the hole position in the middle of this molecule, and then you see how the electron is distributed around, and you clearly see that both the electron and the hole is sitting on the same molecule. So in essence, electron and hole are very close to each other. That's why they feel this Coulomb attraction very much, and this is the reason why they have such a strong binding energy. Now let's the molecule make just a little bit longer, so we go from 2 to 3 rings. And now what happens here? So first of all, of course you can imagine that the molecule is larger, so if you have the hole somewhere, then the electron can go further away from the electron, because the electron distribution now is over a larger molecule. But what this electron-hole wave function also tells you, that's not only sitting on the same molecule, but the electron can also go away and travel to the next molecule. And that way it gets even further away and further reduces the electron-hole binding. And now if you go to longer and longer molecules, we will see that the distribution is over a range of neighboring molecules here. So we pretty much understand why the electron-hole interaction is stronger in smaller molecules than in larger ones. Now let's go to something completely different, and these are 2-dimensional materials. Now this is, what you see here is a stacking of graphene, 1 layer of graphene, which is sandwiched between 2 layers of boron nitride. So why is this important or interesting? Because here we combine 2 materials that are optically completely different in nature. So one of them is a metal graphene or a semi-metal. The other one, boron nitride, is a wide gap semiconductor with a band gap of 7 electron volt or something like this. So you can imagine if you bring these two together, it may be very puzzling to see what the interactions of these mixed systems is, at these interfaces. And this is what we like to explore. Now, interestingly, and this has been found out before, depending on the stacking of this material, you can find superlattices that have a finite band gap. And we're focused on this, and I just want to show you one example here. So this is the stacking where the two boron nitride layers are just in parallel to each other, so they have most interaction between each other. And this you can realize when looking at the band structure. Now the color code tells us what the character of the bands is. So the gray dots here reflect the fact that the low energy range is dominated by graphene. This is actually what we expect, of course. But it also indicates the opening of the gap, which is of the order of 0.3, 0.4 electron volts, pretty independent of the stacking. But you also see that at higher energies, the band structure is dominated by boron nitride, where the valence band comes from nitrogen atoms, and the boron atoms form the conduction band. Now, as I said, these two boron nitride layers, they have the most interaction in this stacking, and that's why we have a pretty large splitting among the conduction bands and the valence band. And you also, this is also reflected in the Conchem densities that you can see here. So here you see the gray bands, they are dominated by graphene, or just represented by graphene. So we have all the electron density in the graphene plane, whereas the valence states, they come from the boron nitride, and you see that the density is all coming from the nitrogen atoms, whereas the conduction band is built by, again, boron nitride, but now the electrons are sitting on the boron atoms. So you can also anticipate from the band structure a little bit what the excitations will be. So in the low energy range, of course, the excitations should be very similar to in graphene, not exactly the same, because we have seen that a band gap opens, and so we can also expect some excitonic effects, and this is in fact what you see here. So the independent quasi-particle approximation and the Bethe-Salpeter equation are similar, but not lying on top of each other. And the high energy range you can expect to originate from the excitations of the boron nitride layers. So this is what we see here. Indeed, very, very strong excitonic effect. So the independent particle approximation is not valid at all, and you have very, very strong peak shifts and redistribution of oscillator strength in this energy range. Now, most interesting for us, because this is really something new, is the visible range in the middle here. And I would like to show you in a minute that these are new excitations that really come from the fact that we put together two very different materials. Nevertheless, let's focus on the low energy excitations first, these excitons number 1 and 2. So what the band structure here tells you, or the color code, these red dots tell you which are the bands that are involved in these respective interactions. So exciton 1 is coming from graphene excitations, as you see. So both the hole and the electron have contributions from the graphene bands. Exciton 2, it's the same, but from a different range in the Brillouin zone. What we also see here, that the exciton is pretty localized in K-space. And so we can expect that it's delocalized in real space, and it has a weak electron-hole binding. And this is what we see, in fact, in the electron-hole wave function. So this is a side view. If we put the hole in the graphene, which we see already it should be there, then you see that also the electron is distributed over the whole graphene plane. If you look on top here, then you see it's very, very delocalized, so it's spread over the whole plane. So this is indicative of very a small electron-hole interaction. Now switch gears, go to the high energy range, and look at these two excitons 5 and 6 here. So 5, you see we have the hole sitting in the boron nitride plane, but in fact at the nitrogen atoms, because these bands have nitrogen character, and the electron again in the boron nitride plane, but now it has boron character. This is seen from the electron-hole of wave function. So now putting the hole at a nitrogen atom in the boron nitride plane, then you see the electron is sitting basically at the neighboring boron atoms, and on the top view you see that the exciton is much more localized than those that I have shown you before. It's even more pronounced for for number 6, where you see that the electron is just sitting at the neighboring atoms and not even goes a little bit further. So the binding strength here is obviously even stronger than in this case. And in fact, we also have to say that it's very similar to bulk boron nitride, which had been shown before by Ludger Wirtz. It's clear. I mean, the bands are formed by boron and nitrogen, so it should be very similar, like in the bulk. But let's go now to the most interesting case, and this is the region, in the intermediate region here. And I would like to point out that these are so-called charge transfer excitations, where the electron is sitting in one plane and the hole in the other, and vice versa. So let's have a look first at the band structure and the character of the electrons and the holes that are contributing to this. Exciton number 3 obviously has the hole in a nitrogen atom, whereas the electron is sitting in the graphene. And exciton number 4, it's the opposite. We have the hole in the graphene, and we have the electron in the boron nitride layer, namely on the boron atoms. And this is what we see also in the exciton wave function. Exciton number 3, the hole is sitting on nitrogen, the electron fully delocalized in the graphene place. Exciton number 4, hole is sitting on graphene, and the electron is delocalized on both planes, because this band has contributions from both of these atoms due to this strong coupling that I mentioned before. So now we have seen a few prototypical examples for electron-hole interaction. Let me now think about or discuss whether we could get these solutions in a cheaper way. And cheaper would be not to go all the way up with many-body perturbation theory, so we need to do GW, we need to solve the Bethe-Salpeter equation, but maybe we can do it alternatively and stay basically in the spirit of DFT. Now, in principle, we could, and there is an alternative, which is time-dependent density functional theory. And in essence, since we are all only interested in the response functions, so in the linear response regime, we could get away with linear response time-dependent DFT. We don't need to propagate the Concham system in time, but just compute the response function. And the key player in this case is the exchange correlation kernel, which plays the same role for excitations like the exchange correlation potential plays for the ground state DFT. Now, as we will see, this is a bit problematic for solids, but there's an example that basically works relatively well. So what we see here is a comparison between the solution of the Bethe-Salpeter equation and time-dependent DFT for the case of gallium arsenide. Gallium arsenide is again a case where electron-hole interaction is not very pronounced, so you don't have strong binding effects, but mainly a redistribution of oscillator strengths. This you see already when looking, for instance, at the random phase approximation and compare it to the Bethe-Salpeter equation. The shape is very similar. The problem here is that the random phase approximation has not been computed from GW, but from DFT. That's why the gap is underestimated. But if you do a GW calculation or apply a shift, then you end up with this spectrum. Now, alternatively, you can use time-dependent DFT. You see TD-LDA, again, is underestimating the gap. And I put it there on purpose, and it shifted, because for molecules, TD-LDA gives you both. It opens the gap and brings the spectra back due to electron-hole correlation. You see, for solids, it doesn't do this. So there's no single kernel that would open up the gap, and that's why it's recommended to do a GW calculation and let the kernel only take care for electron-hole interaction. And there's a few kernels here. This is a static long-range kernel, a long-range dynamical kernel. There is the many-body kernel or nano-quantum kernel, which all give very similar results, but just for this material. And the best one, I would say, is the many-body kernel, but this has been derived from the Bethe-Salpeter equation, and that's why it comes with the same cost. Now, also it looks good for this material. I think there is, I have to warn you somehow to use TDDFT for band gap systems for solids, because, as I said, first of all, there's a drawback that it doesn't open the gap, and second, if the electron-hole interaction is strong, you cannot get everything at the same time. You cannot get the spectrum and the electron-hole binding energy and the dielectric constant at the same time. So you have to choose a kernel which gives you one or the other, but you will never get a good spectrum for these materials. However, as said before, TDDFT is most successful for small molecules, and you can also safely use it for metals. Sorry. And for this, I would like to show an example, just to mention again. So what you have to do in order to get this response function, you start from the Conchem response function, and then you need to iterate and solve the Dyson equation by taking into account here the Coulomb interaction and this exchange correlation kernel. And if you leave out this exchange correlation kernel, then you end up again in the random phase approximation. So you can use both formalisms, the Bethe-Salpeter equation and the time-dependent DFT, just leaving out some terms in order to get the same result. And for metals, in fact, I have to say that very simple kernels like the local density approximation is good enough. You even can leave out, or you can even live with the independent particle approximation in many cases. And this is what I would like to demonstrate you quickly. So what we have done here, we have computed in independent particle TDLDA, gives you the same result. So it's just called DFT. The response, in this case it's the loss function and the dielectric functions for a series of metals. So what you see here in all the cases, and I'm not going into the details, is that overall DFT reflects the shape of the spectra up to very high energies very well. So basically you can live with the DFT band structure and even with the independent particle approximation for the spectra. And so it agrees very well with experiment, but be careful here what experiment you use for comparison, because most of these experiments have been carried out in the 60s or in the 70s, and many of them are not really reliable enough anymore for comparison with a high-level methodology. So in essence, what we learn is that the overall agreement up to a very high energy range is very good, just with a very simple approximation. You need to compare with reliable experiments also in order to challenge your methodology. However, the details of the band structure still matters. And I'll just show you one example here, and this is silver. I mean, what you see is again the mess with the experiments. So we've put together all different experiments, and then you see they're all over the place. However, they agree in one thing, and this is where theory fails, namely this is the onset, the absorption onset in the experimental spectra. So theory underestimates this absorption onset compared to experiment, and of course this is the visible range, and that's why it gives you completely wrong colors. So this would be gold, silver, and copper computed with the BBE band structure. If you do better, if you do GW, then you not only get the right transition onset, but obviously also the right colors. So what we learned from this is that GW may even be needed for metals, just to give you the right transition onsets. In this case, it's the D bands which are strongly localized, and that's why semi-local functionals, they're not supposed to give it, but they even don't give it, so you need GW to correct them. And it's not the electron-hole binding which is crucial in your spectra, but it's more a reliable quasi-particle band structure. Having said this, there's of course also exceptions. Exceptions are low-dimensional systems like graphene, for instance. At high energies, we also have very strong strongly bound excitons. Also carbon nanotubes, even the metallic ones, are very well known for having strong excitonic effects. So now I have introduced to you already our instrument, our code. I'm not going to repeat much, just to emphasize again, since it's an all-electron method, we can also treat the core electrons on the same footing like the valence electrons. We even treat them fully relativistically. And this gives us access to treat also core spectra. And we can use now the same methodology, Bethe-Salpeter equation, in order to compute core spectra from first principles. Now, let's go to the core, and I've picked graphene here because I mentioned that in the valence range, the low energy range of graphene, of course, is dominated by independent particles. It's just direct transitions, but at the high energy range, you may have excitonic effects. Now, if you go to the core, and this is the carbon K edge in graphene that you see, so if you compare the independent particle approach with Bethe-Salpeter, that even the transition onset is dominated by a very strongly bound exciton. So you have a very sharp near edge peak in this material. And this is very indicative for many materials because core electrons are less screened or are more localized, let's put it like this. And that's why in core excitations, electron-hole interactions plays even a more crucial role than in the valence range. And we will see now that the binding energies are even larger than in the valence spectra. So let's abandon graphene and stay with the carbon materials, in particular the organic molecules again. What we have here is azobenzene. Azobenzenes are interesting guys because they are prototypes for molecular switches. So we have these two carbon rings. They have a nitrogen bridge here. And if you shine in light onto these molecules, they will change the structural conformation. And if you shine in light with a different frequency, they will change back to this shape. So this is very interesting for organic electronics. You may use them as switches in devices. However, you cannot use them in a gas phase if you want to let them switch. So in any device, you need to bring them onto a surface. And there's two problems with this, because then people observe that if you bring it on the surface, they don't switch anymore. And there are two reasons why they don't switch anymore. One reason is that they feel the interaction with the surface, and this is why experimentalists don't put them directly on the substrate, but they introduce these linkers in between in order to increase the distance between the molecule and the surface. The other thing is that these molecules, they form very nice self-assembled monolayers. So they pack very efficiently, and we will see that this packing actually affects the excited states, and that's why the switching is hampered or influenced by this. So this is experimental results from Martin Weinel's group. What you see here is the absorption spectrum of such an array of molecules. What we see, a very strong excitonic peak here. It's a pi star transition, and then you have another pi star transitions. This goes to the LUMO, the other to higher excited states. And now, if you compare to experiment, we find exactly the same. So you see, at first glance, independent particle approximation is totally wrong. So you get a very large shift if you switch on electron-hole interaction. You can read here the binding energy is even several electron volts. But most important, just to compare with experiment, we find this by start transitions going to the LUMO at the same place, and also these features here are very nice or resemble those of experiment. Now we are pretty sure that beta salpeter does a good job here. We get a reliable spectra. So let's see what we can learn from them. So what we learned here is, or what we did here first, we compute the optical spectra for 3 different scenarios. One is the molecule in gas phase with vacuum around. The other is the packed SAMs, like experimentalists have grown them. And in the middle, we have what we call a diluted SAM, which only has half the amount of molecules in the, so only 1 molecule in the unit cell. So this is busy, so let me switch off the beta salpeter equation first and just focus on the independent particle solution first. Okay? So what we see here is 3 peaks, A, B, and C, and we can very much understand where they come from. So first of all, we have excited a core hole or a core electron from the nitrogen. So obviously, the strongest interaction will be, and that's why we have a sharp peak, if the electron density is also on the nitrogen. So what we have plotted here is the Conchem wave functions, the Conchem orbitals for this molecule. So obviously, here we have electron density, and this gives rise to this first peak. Now, LUMO plus 1, LUMO plus 2 doesn't have any density at this nitrogen bridge. It's only LUMO plus 3, which has a density here again. And that's why the B peak here comes from an excitation to LUMO plus 3. And the next excitation is given by LUMO plus 7, which gives rise to this peak C here. Now what's interesting is that the independent particle approximation doesn't care about the packing at all. So you have the same peaks in all the 3 structures. And you may ask the question why. Yes, it's clear from a simple point of view, because these are van der Waals bound systems, so there is no density overlap, and that's why the independent particle approximation doesn't care about the packing. But this changes completely now if you switch on the Coulomb interaction. And there you see that these peaks shift very dramatically. We have a binding energy of 6 electron volts of peak A, and around 4 electron volts for peak B and C. But here we see that these peaks shift completely differently depending on the packing. And this brings me back to the aspect of screening, because here we have the most efficient screening. So the binding energy is smallest. That's why peak A shifts least. Whereas in the single molecule, there's no screening basically at all, or very little screening. And that's why these excitonic effects are most pronounced. So my last example, and then I will finish in time, is something completely different. So here we have used core excitations for fingerprinting. This is what core excitations are typically used for. So XANES or XAS experiments are used in order to probe the local environment of a core excitation. We do it here for gallium oxide, which is a very interesting material for optoelectronics. It has a wide band gap. It's used for transparent inorganic semiconductors. So, but it's pretty complicated in crystal structure because it has 10 atoms in the unit cell, and in particular, it has 2 different gallium atoms and 3 different oxygen atoms. When experimentalists now probe the oxygen KH, the core states, they can excite electrons from either of these atoms, and they cannot directly tell us which of the excitations they have probed. So these are experiments done just next door here by Christoph Koch's group. It shows us that this spectrum looks pretty much like a potato, or maybe like the snake that has swallowed an elephant, with these 2 peaks here, and if we do the calculation, then we get something very similar. So I'm not worried about the differences, because the resolution of the experiment is not perfect, and I think we capture these features very well. Now, what is the advantage of this LNES experiment? So we are using here transition electron microscopes, that they can probe different index planes. So they could carry out with different experimental geometries experiments for the 200 index plane, you see here, the plane going through here, and also for 011 going here. Now, if you look at the experimental spectra, you could say, okay, now we have two snakes that have swallowed an elephant, and they both look the same. So what's the difference? Or what's the point here? Now, it's interesting because theory can give insight, because we can probe these different atoms, the excitations from these different oxygen species independently. And if you look up these spectra or decompose them into their compositions, then you see in the first case, these two peaks come from oxygen 1 and oxygen 3, whereas this oxygen 2 only gives rise to this camel-like shape in between. Whereas in the 001 index plane, it's oxygen 1 and oxygen 2 which gives rise to these positions. So that means for simple materials like cubic structures or so, fingerprinting with the experimental probes is very simple. But if you go to more complex materials, you need, or you can combine it with insight from theory in order to explain the local environment of your spectra. So we suggest this combination of theory and experiment as a new kind of probe for fingerprinting structures with more than one species of the same atom, or one types of the same atoms. So this brings me to the end. I want to mention the people who have contributed to the results that I've shown. It's Katharina Kocki, who has been involved in most of the spectroscopy calculations. She's also responsible for the beta package. Dima Nabok is our GW expert in the group. Andres Gulans has also worked on GW. He is one of the main developers and has also sped up the beta code such that you really can use it now for very large systems. Wahib Agun has computed together with Katharina the boron nitride graphene superlattices. Christian Vorwerk has implemented the fully relativistic beta version for core excitations. And I also would like to mention Santiago Rigamonti, who has worked on time-dependent DFT. Needless to say that all the calculations that are involved in the results they have shown are uploaded to the NOMAD repository, so you can look them up. And with this, I would like to thank you for attention.